Imagine handing a researcher $50 and a GPU cluster.
This sounds like a disaster waiting to happen.
Right. So they hit a massive breakthrough on, like, their third experiment. But instead of locking in those new weights and actually deploying it, they just mechanically feed every single winning insight back into the optimization loop.
Just iterating on pure noise.
Exactly. Iterating on noise until they completely degrade the model and just, well, blow the entire compute budget.
Yeah, which is exactly what the world's most advanced AI agents are doing right now when we ask them to recursively improve themselves.
It is wild. And welcome to AI Paper Slop, where we break down the absolute latest in machine learning research. Today, we are tearing straight into a paper from Evolvent AI and the National University of Singapore.
Yeah, it's called RSIBench-Data, Benchmarking Data-Centric Research for Recursive Self-Improvement.
And the core insight here is honestly a massive wake-up call for anyone trying to build autonomous AI researchers.
Yep.
The authors basically built this completely isolated environment to test if agents can improve a model purely through data-centric research. And the result? Frontier agents successfully improved the model from scratch in 58.33% of settings.
Which is huge. They can actually do the research.
They can, but they suffer from this severe discovery reliability gap, because once they hit that peak improvement, 78.26% of agents actually make the model worse if they keep iterating on new feedback.
They just don't know when to stop.
Right. So for all of you engineers out there managing post-training pipelines, in this deep dive, we are going to unpack exactly why these agents overfit to their own validation proxies, the underlying economics of all this wasted compute, and what happened when a frontier model was given $2,000 to recursively improve its own architecture.
Yeah, this premise forces a really serious reevaluation of how we measure progress in AI agents, I think.
For sure.
Because we throw around the term recursive self-improvement, or RSI, as if it's just this inevitable byproduct of scaling.
Like it'll just magically happen.
Right. But true RSI requires a system to observe its own failures, synthesize novel data to correct those failures, and then update its weights without corrupting what it already knows.
Which is incredibly hard. And historically, the way we've evaluated an agent's ability to act as a researcher has been, frankly, deeply compromised by infrastructure noise.
Oh, absolutely.
Like, the paper calls out existing benchmarks, right? SWE-GEM, Datacom, Post-Train Bench. When I look at those, they feel way more like end-to-end system tests rather than, isolated evaluations of a data policy.
They entangle way too many variables.
Exactly. You have agents tweaking learning rates, altering the serving architecture, or just modifying the evaluation pipeline. If an agent produces a better model checkpoint at the end of, say, a data comp run, there is no statistically rigorous way to prove it formulated a brilliant new data synthesis strategy.
Right. It might have just found a hyperparameter combination that happened to play nicely with the specific batch size they were using.
Yeah, it's basically like trying to evaluate a chef's recipe creation skills, but the kitchen appliances, the ingredients, and the oven temperatures just keep randomly changing.
That's a great way to put it. You literally can't tell if the meal was bad because of the recipe or because the oven suddenly dropped 50 degrees.
Exactly.
And if the final metric goes up, you still can't isolate the causal mechanism. For true RSI, the agent has to function strictly as a data-centric researcher.
So what does that actually look like in practice?
Well, it means diagnosing a capability gap. Say the model fails at multi-step Python debugging. The agent has to formulate a hypothesis, generate targeted synthetic training data, and then revise its strategy based purely on the loss or the evaluation feedback of that resulting checkpoint.
Right. No changing the rules of the game halfway through.
Exactly. Because if the optimization surface is constantly shifting, like if the agent is allowed to hack the training script, the feedback signal just becomes utterly meaningless.
And this is where RSIBench-Data comes in. The authors realized they had to completely lock down the entire stack to isolate the agent's data policy.
They essentially built a perfectly stable kitchen.
Yeah, they use a completely fixed-based target model, which is Qwen 3.535B base. The training interface is totally shared and non-negotiable. It's a Tinker-backed LoRa SFT environment.
And then all the evaluation runs through completely isolated, harbor-orchestrated E2B sandboxes.
Right. And those architectural choices are super critical to understand. Using low-rank adaptation, LoRa, for the supervised fine-tuning, ensures that the optimization process is highly constrained.
And computationally predictable.
Exactly. Plus, Tinker standardizes the API so the agent doesn't have to waste tokens writing PyTorch training loops from scratch.
But the E2B sandboxes, I mean, those are the real linchpin here.
Yeah, by forcing the agent to evaluate its synthetic data strategies inside these isolated, secure code execution environments, the benchmark completely eliminates system-level noise.
The agent generates the code, the sandbox runs it.
Right. And the output is deterministic. Plus, every agent gets a strict budget, right? 16 hours of wall clock time and a hard cap of $500 on the Tinker platform.
Which is a pretty realistic constraint.
But I mean, let me push back on this for a second.
Right.
Looking at this from the perspective of an ML practitioner, part of real-world research actually is infrastructure hacking.
Oh, for sure.
If I'm trying to squeeze performance out of a model, I might really need to adjust the gradient accumulation steps or rewrite the data loader to handle a new sequence length. By putting the agent in this totally rigid box, aren't we basically handicapping its ability to find the creative engineering solutions that actually lead to state-of-the-art results?
I mean, if the goal were simply to produce the absolute best possible Qian model, you'd be right. But the goal here is auditability.
Oh, okay.
By channeling all the data submission, the training, and the evaluation through that impenetrable harbor boundary, the entire feedback loop becomes a closed, fully measurable system.
So we can attribute every single fluctuation purely to the data.
Exactly. We can attribute any performance difference strictly to the agent's generated dataset. There is zero room to mask a misaligned data distribution with some clever post-training hack. The benchmark forces the agent to answer one very specific question. What data does this model need to see to get better?
Okay, that makes a lot of sense. So let's look at how the heavyweights actually handled that question. The authors dropped Claude Code Opus 4.8 Sonnet 5 and Codex GPT 5.6 Sol and Terra into this lockdown environment.
The heavy hitters.
Yeah, and they tested them across 6 major benchmarks: SWE Bench Verified, Multilingual, Pro, Terminal Bench 2.0, GPQA Diamond, and A.
And these are not trivial data curation tasks.
Not at all. SWE Bench requires reasoning across massive multi-file code bases, while AIM requires incredibly strict mathematical deduction.
And the initial success rate they saw is a massive signal for the industry. Like you mentioned earlier, in 58.33% of the settings, these agents successfully analyzed the baseline failures, synthesized a novel dataset, ran the LoRa SFT, and actually produced a model that scored higher than their first valid attempt.
That's wild. So they aren't just regurgitating static data sets from their pre-training.
No, they are dynamically generating aligned supervision tailored to the specific capability gaps they diagnosed in the Quinn base model.
Okay, so that 58% success rate basically proves the fundamental mechanics of agent-driven RSI are viable today. But the drop-off after that initial success is the core bottleneck that this paper exposes.
Yeah, the plot twist.
Right, because once these agents hit their peak improvement, they don't just plateau. In 78.26% of cases, if the agent continues to iterate based on new feedback, the final checkpoint is actually worse than the peak.
They actively degrade the model they just improved.
It's basically like a gambler at a casino who hits a massive jackpot but has absolutely no concept of when to walk away.
That is a perfect analogy.
They just continually pump the winnings back into the slot machine until they degrade their own baseline and walk out broke.
And this non-monotonicity is probably the most mathematically fascinating part of the research. It exposes a really severe flaw in how current frontier models process iterative feedback.
What's actually happening under the hood there?
Well, when an agent observes a new error log from the sandbox, it attempts to revise its hypothesis, right? But instead of refining the overall data distribution, it frequently synthesizes a new training set that suffers from catastrophic forgetting.
Oh, so it over-indexes on the most recent error.
Exactly. It's essentially overfitting to its own validation proxy.
So an agent might see the model fail a specific Python syntax test in the E2B sandbox, and it reacts by generating thousands of synthetic examples focused purely on syntax correction.
Yep. And when that new data goes through the LoRa update, the model weights shift so aggressively toward syntax that it just forgets the deeper algorithmic logic it learned in the previous iteration.
Wow. And the trajectory logs in the paper actually confirm exactly that mechanism, right?
They do. The agents basically suffer from what we can call reward hacking of their own internal evaluator. They misdiagnose the root cause of a failure. They generate supervision that optimizes for a really shallow proxy of the task, and then push that misaligned data right into the training loop.
And worse, they often search right past highly capable checkpoints because their internal evaluation fails to recognize that the new hypothesis is actually weaker than the old one.
Exactly. And task fragility heavily influences this behavior too. There isn't a single master researcher agent yet.
Right, like Codex GPT 5.6 Sol won the three non-SWE benchmarks, Terminal Bench, GPQA, and AIM. But the three SWE bench tasks, which are heavily focused on software engineering, were won by three entirely different agents.
Yeah, the architecture of the specific agent interacts heavily with the geometry of the task environment. Like, Codex might possess a pre-training distribution that makes it exceptionally good at synthesizing the strict logical steps required for AIM math problems.
But is WE Bench requires tracking variables across dozens of files and understanding complex system states.
Right, so an agent that excels at generating self-contained math proofs might just completely fail to generate coherent, multi-file synthetic data for a SWE bench task. The capability is hyper-localized.
And this hyperlocalization, combined with that tendency to degrade baselines, creates a massive economic problem. I mean, if you are running an ML team, compute is your most precious resource.
Oh, absolutely.
You cannot afford an automated pipeline that burns GPU hours training actively harmful checkpoints. So if we look at the raw numbers here, what is the actual cost of this search process?
Well, the median run produced 4.5 valid candidate models, and that required a median of $62.51 on Tinker, taking about 6.55 hours of wall clock time.
Okay, that doesn't sound too bad for a single run.
No, but because these agents lack a reliable stopping condition, the tail end of the distribution is brutal. Some runs churned out 15 candidate models, eating up nearly 16 hours and costing over $360.
Wow. And if you extrapolate a $360 cost for a 35 billion parameter model just doing simple LoRa updates, I mean, scaling this process up to full parameter tuning on a frontier class model would bankrupt a research lab in days.
It really would. The wasted compute is staggering when 78% of those later iterations are producing worse models.
So is there any saving grace here?
There is, actually. The only thing preventing this from being a total systemic failure is the agent's ability to utilize a checkpoint selection rule.
Okay, how does that work?
Well, while their discovery policy is flawed, their selection policy shows some real discipline.
Yeah.
Before the official evaluation against the held-out test set, the agents review their internal sandbox logs and explicitly select their historical best checkpoint.
Oh, so they might generate 15 models, realize model 6 through 15 are garbage, and just submit model 5 as their final answer.
Precisely. In Terminal Bench, for example, Wren spent up to $96 after hitting their peak performance without ever improving the score again.
Just burning cash.
Just burning cash.
Yeah.
But because the agent reverted to an earlier checkpoint, that wasted $96 didn't actually corrupt the final official evaluation.
Ah, okay. So stopping rules are just as important as discovery rules. If your automated researcher is prone to non-monotonic degradation, your checkpoint preservation architecture has to be rock solid. Now, the paper also explores a potential fix for this degraded hypothesis generation, which is basically just letting the agent think longer, right?
Yeah, the reasoning effort experiment.
Yeah. They ran this with Claude Code Sonnet 5 on SW Bench Verified and bumped the API setting from high reasoning effort to max reasoning effort.
And the results of that single parameter change are incredibly revealing about how synthetic data generation actually works. Bumping to max effort raised the very first candidate's selection score from 25% to 36%.
And the official final score jumped from 35% to 52%.
Wow, a 17% absolute jump.
Which is crazy, right? Just by increasing the token budget for reasoning. But what is mathematically happening under the hood there? Because it's not just thinking harder.
No, it's trading search breadth for higher candidate quality through deeper static analysis.
Okay, unpack that a bit.
So when set to high effort, the agent might quickly scan the error log, take a guess at the problem, and rapidly generate a batch of synthetic data. It's a pretty shallow hypothesis. But at max effort, the agent allocates a massive token budget to chain of thought processing. It simulates the execution steps, it rigorously validates its own proposed supervision against the error trace, and, crucially, it prunes bad logic before it ever formats the data for the LoRa SFT.
So it's shifting the compute expenditure from the post-training optimization loop back into the inference time generation loop.
Exactly.
Instead of throwing a dozen cheap, noisy data sets at the GPU and just hoping one sticks, it spends the compute up front to formulate one highly accurate, validated data set.
Which, given the cost of GPU hours for training versus token cost for inference, That seems like the necessary path forward for RSI economics.
It absolutely is. But I mean, even with max reasoning effort, everything we've analyzed so far is an asymmetrical relationship, right?
Yeah, it is.
The frontier agent, whether it's Claude or Codex, is acting as the researcher to improve a smaller, less capable model, which is Quen 3.5. It's essentially like a graduate student tutoring a freshman.
That's a good way to look at it. But the real test of recursive self-improvement is whether a model can patch its own flaws.
Yes. And the paper tackles this head-on with their exploratory experiment. They set up a Claude code harness powered by the Kimi K 2.6 model and tasked it with improving the instruction-tuned Kimi K 2.6 model.
So is the agent looking at its own architecture?
Exactly. Diagnosing its own behavioral flaws and attempting to synthesize data to expand its own capabilities.
And they gave the agent a massive resource ceiling for this, right?
Yeah.
Like a $2,000 budget and over 12 hours of processing time.
Yeah, $2,000 and 12.3 hours. And the result was, well, a complete failure.
Totally flatlined.
Despite the compute, the budget, and the time, every single checkpoint the agent produced remained below the 33% unadapted reference baseline of the original model. It literally couldn't beat itself.
And the mechanics of this failure come down to a severe ceiling effect on the proto-frontier.
Meaning the target model was already too good.
Basically, yeah, Kimi K 2.6 is already a highly optimized, heavily instruction-tuned artifact. When the agent was improving Quenbase, it was operating in a space full of low-hanging fruit.
Like basic formatting and alignment.
Right, which the agent easily synthesized data to fix. But with Kimi K 2.6, the easy gains are already baked into the weights. To improve a frontier-level model, the researcher agent needs to discover a training distribution that pushes the model in a genuinely novel gradient direction.
And that requires insights the agent's current weights simply don't possess yet.
Exactly. If the agent's internal world model is only as sophisticated as Kimi K 2.6, it cannot generate synthetic data complex enough to teach Kimi K 2.6 a concept it doesn't already know. It's trapped by its own representation limits.
So it attempts to generate new data, but because it can't evaluate ideas beyond its own intelligence ceiling, it ends up generating supervision that slightly misaligns the highly tuned base model,
resulting in a degraded checkpoint every time.
Wow. Now this does highlight a crucial limitation of the RSI-Bench-Data study and really of the whole field right now.
Yeah, the fixed task subsets.
Right. The benchmark rigorously tests how well an agent can optimize for a specific flavor of set WE bench, or AIM, but it doesn't measure full statistical generalization to completely held out domains.
Which is a pretty big blind spot.
Yeah.
If an agent successfully synthesizes a dataset that boosts SW bench scores by 10%, we know it solved the immediate capability gap.
Yeah.
But because the evaluation is constrained, we don't know if those resulting LoRa weights caused catastrophic forgetting in an entirely unrelated domain, like, say, medical literature analysis or creative writing.
Right. We need evaluated private splits and continuously refreshed tasks to prove these data strategies are actually producing generally superior models rather than just overfitting to the benchmark's specific environment.
Exactly. Future iterations of this benchmark will definitely need to address that.
But even with those limitations, I mean, RSI-Bench-Data gives the industry its first truly auditable, noise-free metric for automated ML research. The dream of spinning up a server farm, turning on an agent, and letting it infinitely self-improve until it hits superintelligence is definitively bottlenecked.
Yeah, we're not there yet.
Frontier models have the spark, right? They can write hypotheses, they can successfully synthesize data to improve smaller models in, 58% of cases, but their inability to reliably turn iterative feedback into stronger strategies without backsliding into degraded baselines, that is the current wall.
The capability to discover new knowledge is present, but the systemic reliability to manage long-horizon research without corrupting existing knowledge is just entirely missing.
And that leaves us with a final concept to consider for you all listening. We spend all of our time in ML focusing on generation, right? Generating new data, finding new hypotheses, adding more parameters. But if these AI researchers consistently degrade their models by over-iterating on noisy feedback, perhaps the missing mathematical ingredient for recursive self-improvement isn't just synthesizing new data.
That's a really interesting point.
Think about how human experts learn. Mastery requires aggressive pruning. It requires the ability to recognize a false assumption, discard a bad habit, and explicitly unlearn corrupted pathways.
Yeah, you have to know what to throw away.
Exactly. If we want AI to recursively improve, we might need to stop focusing purely on data generation and figure out how to teach an agent the incredibly human, highly complex, systemic skill of forgetting. Because if an agent can't learn to aggressively prune its own bad hypotheses before they infect the training loop, it will never survive the search process.
Just keep chasing its own tail.
Exactly. Keep questioning the benchmarks, watch your compute budgets, and we'll see you next time for another deep dive on AI paper slop.